So far, we have introduced 4 different tools for analyzing signals and systems. Those tools are the Fourier series and the Fourier transform for both the discrete time signals as well as the continuous time signals. In this module, we are going to introduce a new tool called as Laplace Transform. This tool is very beneficial for analyzing signals and systems. Now, before going ahead, let us give a thought that whether the tools which were already introduced, aren't they sufficient enough? Is there really a need to go for a new tool for analyzing signals and systems? Let's try to answer these questions in this module. Let's take an example. I'm taking an example of a signal, say for example x of t equals to, so I'm taking an example of a signal x of t equals to say e power 2t u of t. So I have deliberately chosen this example to demonstrate the need of Laplace transform. Now, how does this signal look like? So if we try to visualize this signal looks something like this. So the signal is appearing to be going something like this. What is this? This is the signal that we have considered here. That is x of t. So this is x of t with this t variable here, and this is of course 1. You can see that this signal is going out of bound, so this is not absolutely integrable here, and due to that we may not be able to find the Fourier transform of this signal. What I mean by that is, if you remember the Dirichlet conditions, the essential condition, the conditions that are required for the existence of Fourier transform, we said that the signal must be an absolutely integrable in order to find its Fourier transform. So this signal that we have considered here is not absolutely integrable, and hence we cannot calculate the Fourier transform. So I can show you that demonstration here. So if I attempt to calculate the Fourier transform, let's see what happens. So if I try to calculate the Fourier transform, we know from definition it is going to be x of omega equals to integration from minus infinite to infinite this x of t e power minus j omega t dt, and that is going to be integration from 0 to infinite, just because I have multiplied this signal by u of t, so limits will be from 0 to infinite e power 2t times e power minus j omega t dt, and this is going to be equals to integration from 0 to infinite e power 2 minus j omega times t dt, and this is going to be equals to e power 2 minus j omega t divided by this coefficient 2 minus j omega, where this limits that we have to substitute is 0 to infinite. And if I try to simplify this further, this is going to be e power 2t times e power minus j omega t divided by the same factor here, that is 2 minus j omega, and the limits from 0 to infinite. Now if I try to substitute, if you attempt to substitute this infinite here, you can see that this term here is going to be infinite, and therefore this complete expression, we are not able to find any expression for this x of omega. You can see that this term here is a kind of complex number in the form of r e power j theta form, and if this magnitude turns out to be infinite, this expression here x of omega, we may not be able to find any expression for this x of omega. So this expression here tends towards infinite. That's what we were saying, that if a signal goes out of bound, or if it is not absolutely integrable, we cannot find the Fourier transform. So let's try to analyze when are we going to find the Fourier transform, when are we able to find the Fourier transform. So as we said that the signal, only if it is absolutely integrable, then only we will be able to find the Fourier transform, just because this integration in that case is going to converge. Now let's observe how are we going to make this signal absolutely integrable. You can see that this signal is going out of bound here just because it is e power 2t, and in order to make this signal absolutely integrable, we must modify this signal somehow such that this signal converge. So let's make an attempt to converge this signal. What I'm doing here is that this original signal x of t, I'm multiplying this signal x of t, that is e power 2t u of t. I'm trying to multiply this signal with a factor such that this original signal is going to get converged. Now you may see from here that, let's suppose if we try to multiply this signal by a factor of say e power minus 3t. So what I mean by that is, suppose I multiply this signal, so this original signal I'm trying to multiply by a factor, say, so let me modify this signal, let this be x dash of t, or let it be x modified version, let that be x dash of t. That's not a derivative, it's simply a different signal. So let me denote that with any other variable, so let that be y of t. So I'm having this signal y of t, that is this e power 2t u of t times an additional factor there, let that be e power minus 3t. So I've multiplied the original signal here, that was e power 2t times u of t, by an additional factor, that is e power minus 3t. So what will happen, this e power 2t will get multiplied with e power minus 3t, giving us e power minus t, and that signal is going to get converged. So somehow what we are trying to do is to modify, or we are going to tweak this signal such that the signal is going to get tapered, or it is going to get converged. If we do that, the signal is going to be absolutely integrable. What I mean by that is, if I try to plot this signal, this new signal here, this new signal is going to be something like this. So this is going to be y of t, and just because this signal is now inbound, or you can say that this is absolutely integrable, we are able to find its Fourier transform. Let's try to do that. So if I try to attempt to calculate the Fourier transform, so it is going to be y of omega, it's going to be integration from minus infinite to infinite y of t e power minus j omega t dt, and from the previous calculation you can see that this is going to be from 0 to infinite. This is going to be e power minus t times e power minus j omega t dt, and this is going to be equals to from 0 to infinite e power minus 1 plus j omega t dt. This integration is going to be e power minus 1 plus omega t by minus 1 plus omega from 0 to infinite. This j is going to be equals to, you can see that this is going to be e power minus t times e power minus j omega t by this 1 plus omega, and limits from 0 to infinite. And now if I try to substitute this limit of t here, that is infinite here, you may see that e power minus infinite is going to get converged, that is going to be getting 0. So this is going to be equals to 0 minus, and if we try to substitute this 0, it is going to be 1 divided by this minus 1 plus omega, and this expression turns out to be 1 upon 1 plus omega. So what has happened here, this original signal for which we were not able to calculate the Fourier transform, if somehow we try to multiply or try to taper or modify that signal such that the signal converges, then we are able to find the Fourier transform here. You can see that here. It is going to be 1 upon 1 plus 1 plus omega. So what have we done? We have simply taken a signal and we have tried to multiply that with an exponential factor here. That exponential power is a negative higher than the exponential power of the original signal. What I mean by that is the signal is going to converge even if we take anything e power minus something higher than this term here. So let's suppose if we take e power minus 40, then also we are able to find the Fourier transform. If we take e power minus 5t, then also we are going to find the Fourier transform. So this multiplication factor should be such that this term e power minus something, that something must be higher than the term here, the original signal here, so that the combined effect after multiplication, we are going to get a signal that is going to get converge, or we should be able to get a signal that is absolutely integrable. So you can see that this factor here must be stronger, or it should be stronger in opposite direction, such that the combined effect must be converging. So what we have done here is that the original signal we have multiplied with this additional factor here, and we have taken an example of this e power minus 3t, and not necessarily for 3, we can take any number higher than 2. Even if it's 2.1, still we are going to find this expression here, 2.1, 2.2, anything higher than 2, of course in negative power, then this expression is going to converge. So let's try to generalize this fact. So what we have done here is that x of t, if it is going out of bound, or if it is not converging, we are trying to multiply this with an additional factor here, that is e power, let's say minus, let's say in general let it be sigma t, and then try to calculate its Fourier transform. So this complete term after multiplication, we are trying to calculate the Fourier transform, that is e power minus j omega t dt, and this integration going from minus infinite to infinite. That is what we have done. So we have this additional factor here, and the expression otherwise remaining, so apart from this factor, the remaining expression is simply the Fourier transform. So if we write that in more compact form, this is going to be equals to minus infinite to infinite x of t e power minus this sigma plus j omega t dt. Now you can observe this is a kind of complex number. The sigma is a real number and this j omega is the imaginary part of this number. So this quantity, let's have this quantity here, this complex number. Let's rename this complex number, let it be s, that is sigma plus j omega. This is a complex number. So that expression is going to be equals to minus infinite to infinite x of t e power minus st dt, and the expression that we have obtained here is called as the Laplace transform. Now this is not now the variable of omega, is now the variable of s, so we have to write it as x of s. So the expression that we have just obtained is called as the Laplace transform. So what's new here? The new term here is simply the e power minus sigma t term. So this Laplace transform, if you observe that this Laplace transform is closely related to Fourier transform. In fact, it is a generalized version of a Fourier transform. So if we have a signal, if we try to taper that signal, or if we try to multiply this signal with e power minus sigma t and then calculate the Fourier transform, it is going to be the Laplace transform. In fact, this Laplace transform, if you make this sigma factor, that is this s, the real part of s, if you try to make it 0, it is going to give you the Fourier transform. So let me write that. So Laplace transform, this is Laplace transform. And we can see that the Laplace transform, let it be LT. So Laplace transform for sigma equals to 0 will give the Fourier transform. Which Fourier transform? It is of course the continuous time Fourier transform. It is going to give the continuous time Fourier transform. So the Laplace transform evaluated at sigma equals to 0 is going to give you the Fourier transform. So what this Laplace does? The Laplace simply try to find the suitable attenuation factor after which this integration is going to converge. That's it. So this new tool is simply a kind of generalization of the Fourier transform that we have already learned. So let's take the same example and try to calculate the Laplace transform. So the same example, if I try to take that example, so let's take same example. So this x of t is e power 2t ut. So this capital x of s is going to be integration from minus infinite to infinite x of t e power minus st dt. So that is going to be some integration from 0 to infinite e power 2t times e power minus st ut. So ut will be is already covered here, it will be dt. It is going to be e power minus s plus 2 times t divided by this minus s plus 2 from 0 to infinite. And this is going to be, now let's try to replace this s by sigma plus j omega. That is going to be e power minus, so I'll write that as minus sigma minus j omega plus 2 t dt divided by this, so I'll keep s as it is here. So this is due to the fact that s is sigma plus j omega, and what we are going to get is equals to, now of course the limits, so we have forgotten the limits here, no dt here, so there's no dt because the limits are going to be 0 and infinite. So this is going to be e power, so let me separate out the real parts here. This is going to be e power minus sigma plus 2 times t times e power minus j omega t and divided by this minus s plus 2 factor with a limit of 0 and infinite. Now let's see what happens if I try to replace these limits here. So this t we are replacing by infinite, and you can note that this expression in that case, so if I replace this infinity here, this is going to be 0. This term is going to be 0, and therefore this term is going to be whole as 1. And what if I replace this t as infinity here? Now this expression is going to converge only if this factor in the parenthesis, that means minus sigma plus 2, is negative. If that is negative, then only this expression is going to get converged, because in that case the expression would be 1 upon this 2 minus s, or minus s plus 2. Otherwise this is not going to get converged. So what I mean by that is the expression is going to converge. So let me write that this factor here must be negative, just because when it is negative, after substituting by infinity here, this is going to get some value. I mean, apart from infinity, it is not going to shoot to infinite, because if this term is negative, if I replace this t with infinity, so e power minus infinite, it is going to be 0. So in that case, this signal is going to get converged. This x of s is going to get converged. If it is positive, if this term is positive, then it is going to be e power infinite, and everything is going to be infinite in that case. So this term is going to be, so I'll write that term step by step. So this is going to be equals to 1 upon this minus s plus 2 times e power minus sigma plus 2 times this infinite, if I try to attempt that, and e power minus j omega times infinite minus e power 0, so that is 1 here, minus sigma plus 2 times 0 times e power minus j omega times 0. So you can see that this term here must be negative, then only this expression is going to converge. The other terms are not a problem, because this term, so let me make this term, so this term here is going to be 1, this term here is going to be 1, so it is going to be minus 1 in total. This term here is going to be 0. And what about this term? This term is going to get converged only if, so this term is going to be converging only if, so let me write that converge only if this factor here minus sigma plus 2 is negative, that means less than 0. So what we are going to get is that the expression is going to be equals to 1 upon, so you can see that this minus 1, this expression after substituting this infinite, and let's assume that this term here is negative. If that is negative, e to power minus infinite then this term is going to be, you can see that this term is going to get converge, and the expression that we are going to get is can see that this expression is going to be 1 upon, you can observe that if this term goes to minus infinite, this term whole is going to be 0, and what we are left with is minus 1, and this minus 1 is going to give you it's going to be 2 minus s, or s, this is going to be 2 minus s here. You can see that this expression here, this 2 minus s with again the minus sign, that is going to be, so I'll write it directly, so it is going to be s minus 2 here, s minus 2, and this expression is, it is going to be this expression only if we have just noted this factor, this minus sigma plus 2 is less than 0. So minus sigma plus 2 is less than 0, or we can say that the sigma is higher than 2. So that is the condition for the convergence, and this condition is also called as the region of convergence condition. Is also called as region of convergence condition, because you can see that this expression is true only if this condition is satisfied. So this expression is true only if this condition is satisfied. So what does it mean in a physical sense? As you can see in this example, this is e power 2t, and we said that this sigma must be higher than 2. That means, as we have said this in this example, in the earlier case, this we have tried to multiply this signal e power 2t by e power minus 3t. So just because this sigma was higher than this factor here 2, therefore we were able to calculate the Fourier transform. So that's what it means here. The sigma factor higher than 2 is actually reflected here in this example. This is the sigma. This is because e power minus sigma t, so this sigma must be higher than this 2. So anything you can take, e power minus 4t, e power minus 5t, 10t, 100t, and so on. So whenever this sigma is going to be higher than this factor here 2, then the signal is going to converge. That's what is the meaning of this term here. We are going to get this expression only if the sigma is going to be higher than 2. Now that is what is called as I said, is called as the condition for the existence of this Laplace transform, or it is called as the convergence condition. We shall see more into this in the next module. See you then.